The leader has muted your line. To unmute your line, press #6.
Ready? Questions? Hi, everybody. Welcome to this afternoon's webinar. This is Laura McKelvey, and I'm going to go through some of the logistics. Thanks for joining us. Today's webinar is an overview of how we conduct regulatory risk assessments here in the Office of Air Quality Planning and Standards. And just to go over some logistics to start off with. We've got your phone lines displayed if you are calling in. If you're not calling in through the phone line, please make sure you mute your computer so you don't hear feedback from both the phone line and the computer. If you have trouble with the connections, it's best to sign off and then sign back on. If you still have trouble, shoot us a question in the question and answer box, and we'll try to resolve it from our end. If you want to see the presentation in full screen, there's an icon on the top right corner of your screen that has 4 arrows pointing away from each other. If you click on that icon, it'll make your screen a full screen, but you will lose the question and answer box. If you want to shrink down and ask a question, then go back up and hover over that same spot. The icon will appear, click on it, and your screen, it'll reduce the screen and bring up the quick question and answers. As we typically do in our webinars, we'll wait till the end to ask questions, and we will capture the questions at the end and work through them as we can. So with that, I'm going to turn it over to this presentation to Kelly Rimer, and she's going to walk us through today's webinar.
All right, thanks, Laura. Again, my name is Kelly Rimer. I'm the group leader for the Air Toxics Assessment Group here at EPA in the Office of Air and Radiation. Our group is responsible for doing the risk assessment of the Air Toxics Program and also the National Air Toxics Assessment. The phone, there may be some. There we go. All right. So I'd like to thank everybody for joining the call this afternoon. I'm going to walk through the general approach that we use in this office for conducting a risk assessment for the pollutants called the air toxics pollutants. Our hope is that this background information will be useful to you when you hear about the risk results next week and when we have future conversations about risk. So we'll start with the overview. We'll do a couple slides that you've seen before if you were at the Air Toxics Regulatory 101 a couple weeks ago, as a reminder for folks and for new folks coming in as some fresh information. So what are air toxics? We'll define what a risk assessment is and the type of risk assessment that we do. We'll walk through the risk assessment steps. We need to understand someone's exposure, how much of the pollutant you're breathing. We also need to understand what health effects are caused by that pollutant. And you put that information together and we do the final step, which is called a risk characterization, where we estimate the risk. And then finally, we'll walk through a couple of slides about how to read our risk assessment results. We'll do an example calculation. We'll show you a risk table that may be similar to a risk table you'll see soon, and also a graphic that we use to help folks understand the risk. So what are air toxics? So air toxics are also known as hazardous air pollutants. That's actually what the Clean Air Act calls them, HAPs. EPA regulates 187 different air toxics and air toxics chemical classes. So there's a lot more than 887 pollutants because there's several forms of, like chromium, for example. These pollutants may cause cancer and other serious health effects. And the Clean Air Act does specify how EPA must regulate air toxics, and they're regulated differently than the pollutants called the criteria pollutants. For criteria pollutants, EPA regulates a level in the air that should not be exceeded. For air toxics, the Clean Air Act doesn't direct EPA to set limits for the amount that's in the air. What it does is it requires EPA to set standards for the emissions of air toxics from industrial facilities. So it's what they can emit into the air. There are limits on that, not what's in the outdoor air, what we call the ambient air. So there's a little difference between those programs. Examples of air toxics emitters can range from huge facilities like petroleum refineries or big chemical facilities, and down to the dry cleaner and the gas station down the block. So air toxins can cause cancer. In fact, more than half of the 187 pollutant classes are known or suspected to be human carcinogens. Many others are known to cause respiratory or neurological or immune or hormonal or reproductive system effects. These pollutants have different physical and chemical characteristics. For example, some are particles and some are gases. We can be exposed to these pollutants in multiple ways by breathing air, and that's what we will focus on in this assessment, in this methodology that I'm talking about. But we can also be exposed by eating contaminated food products, for example, fish or fruits and vegetables that are grown on contaminated soil. We can get it through contaminated drinking water, having skin contact with soil, dust, or water are all ways that we can be exposed to these pollutants. They have the potential to cause adverse environmental effects on plants and critters. Some of them persist in the environment, or they can bioaccumulate, meaning that they can get more concentrated as they move up the food chain in different kinds of animals or plants. And also some of them can be, most of them, all of them are transported locally, but some can travel further, like regionally or nationally or even globally. So it's a wide range of characteristics that these air toxins have. So now let's talk a little bit about risk assessment. So what is a risk assessment? Well, it's a systematic process for evaluating the potential risks that may result from an activity. In this case, the activity we're talking about is exposure to air toxics, and again, this talk will focus on breathing the air. The exposure is inhalation. We use these risk assessments here at the EPA to characterize the nature and the magnitude of the health risks, and to make policy decisions and to set regulations. So what's cancer risk? Well, cancer risk refers to the probability or the chance that exposure to an air toxic is going to cause cancer. Typically what we do at EPA is we estimate the risk from a 70-year exposure from a given facility, and what we then end up with is the risk which is on top of or in addition to our overall risk of getting cancer. And so the technical term we use for this is lifetime excess cancer risk. So as I just said, the risk assessment is the systematic process for evaluating risk, and it's designed to help us understand and make sense out of a real-world situation and try to understand what somebody's risk is. So what I'm going to do in the next couple slides, I'm going to talk about the real-world situation and then how the risk assessment evaluates that real-world situation. So here's a graphic that very simply describes what happens when people are exposed to air pollution. You'll see in the left side this box looks sort of like a facility, and it's labeled source. So first, the pollutants are emitted from an industrial facility or source. You'll see that there are emissions that are coming out from the top of the building from a stack, and this represents emissions that are usually have passed through some sort of air pollution control device. And what those devices do, obviously, is they lessen the amount of the pollutant that can enter the air. There are also some emissions that are coming out of the building sort of lower, out of a window maybe, or some sort of vent, and these are referred to as fugitive emissions, fugitive because they escape. They usually have not been passed through a control device. They're also emitted closer to the ground, so they won't dilute as fast as emissions that are released out of the stack. So close into the building, those concentrations can be higher for a fugitive emission than an emission coming out of the stack. The next thing that happens is wind takes the pollutant and it moves it across. It disperses it. And that's what we say by dispersion. And through dispersion, the pollutant becomes more dilute. Typically, the further away we are from the facility, the less concentration is the pollutant. The next step, of course, is then we inhale the pollutant, and then it gets into our bodies, we intake it, and then as it can move around to different organs, and we refer to those as target organs. And the end result can be adverse effects such as cancer or non-cancer effects. So that's what happens in the real world. So again, a risk assessment uses specific analyses to help us understand what the real world risks are. And there are 4 parts: planning, doing the exposure assessment, then we have the toxicity assessment box there, and then the risk characterization box on the bottom. So when we're planning a risk assessment, we ask specific questions in the exposure assessment box and the toxicity assessment box, and this ensures that we're answering the right question. We have to plan what we're going to assess. We're going to have to plan what metrics we're going to use. We want to make sure that we're doing the right analyses to get the answer to the question that we really want to know the answer to. So the questions that we ask on the exposure side for this kind of assessment is fairly straightforward. How much of the pollutant are people exposed to during a specific time period? And the questions we ask on the toxicity side is, what health pollutants can the pollutant cause? What health problems can it cause? And then what are the health problems at different exposures? How toxic is it to us? And that's a numerical understanding. And then in the risk characterization, we want to know what's the extra risk of health problems in the exposed population over the period of time that we're interested in. So that's how we plan it. We ask these questions. And then what we do is we do specific analyses and have some specific inputs and then outputs for the risk assessment. And so we'll go through all of these separately. But for example, for exposure assessment, we need to have a good understanding of emissions, and then we do air dispersion modeling to get the concentration that we care about, the concentration where people are breathing. When the kinds of analyses we do under toxicity assessment is we have to understand, again, what health effects does the pollutant cause cancer effect and non-cancer effect, and then we have a numerical estimate of toxicity that's developed. And at the end of the day, for air toxics risk assessment for cancer, we multiply exposure times toxicity, and we get the cancer result. So just stay on this one for just a second. So the next couple slides, we're going to talk about the kinds of inputs and analyses we do under the exposure assessment part. So we can go to the next slide. Great. So we need a couple of things, as I mentioned. We need to understand the emissions. So there's a couple of different kinds of emissions I alluded to in one of those earlier slides. We have stack emissions. Sometimes we call those point source emissions. They're usually elevated above the ground. They're usually estimated using operations data or emissions factors, or they're measured using monitoring techniques. Often, like in the case of Willowbrook, we actually did some monitoring and really got a better understanding of what the emissions actually were. Monitoring is a better way to do it than using calculations. So we're glad we had that in this case. Fugitive emissions, again, are usually emitted much lower to the ground from vents and windows. There's not a real single point with which to measure it, so it's a little more difficult to measure. So usually we estimate using emission factors and chemical and engineering, and sometimes we use monitoring techniques. And again, at the Sterigenics site here, in this case, in your area, in Willowbrook, we used monitoring techniques to get at those fugitive emissions. So once we understand what the emissions are, we put those into a dispersion model along with some other information. So what's a dispersion model? So it's a computer simulation that moves a pollutant through time and space. So the inputs that we use, again, we use emissions both from the stack and from the fugitive. We need to know about the pollutant, the chemical information. Is it a gas? Is it a particle? We also need to know how hot the exit is coming out of the stack and how big of a diameter it's coming out when it's coming out of the stack. Then we also use meteorological data wind, cloud cover, things like that. And then we also use terrain. Sometimes we call that topography. Is it a hilly area? Is it a flat area? And those all go into the dispersion model. And the output is a concentration at what we call receptors, which are distances that are predetermined, that we know where they are, and we can assign these receptors around the model. We call that the modeling domain, and it's 50-kilometer radius. So if the plant's in the middle of a big circle, the model will go out 50 kilometers or a little over 30 miles in each direction in a bigger circle. So the outputs, again, are the ambient concentration at a receptor and for a given time period. And usually we use like the average annual concentration. We were looking at about what we like to look at as a year's worth of data. So why do we use dispersion models? So dispersion models are good because they can predict both short-term and long-term pollutant levels in the outdoor air. So we can say, well, what's the concentration at an hour, for example, next to this facility, or the highest hour of the year, or the highest series of hours during the year, if we're looking at a pollutant that we're concerned about for a short period of time, if you're breathing it for a short period of time. Then we can also look at longer-term levels. Like I said, we usually do up to a year. We can place the receptor wherever we want. That's another good reason to use the dispersion modeling. Monitoring is great, but we only know the concentration at those monitors. When we use models, we can put receptors wherever we want to in the whole domain and have a good idea of what those concentrations are. So there's a lot more data to work with when you use a model. And then we can predict levels under a wide range of conditions, typically over a full year. And again, that gives us a richer data set. And then we can use, what-if scenarios. We can say, okay, well, we've got a baseline risk estimate of a source that's not controlled at all. And then we have two options that two different kinds of pollution control equipment we could put on a source. So we can use the model to say, well, what are the concentrations going to be off-site if we use option A or option B? And that helps us choose, when we're setting regulations, the best air pollution control equipment that we can put on a facility. All right, so that was a little bit about the key inputs in the analysis that we do when we're trying to get an idea of how much a person breathes of the pollutant. Now we're going to move to the toxicity side, the toxicity assessment. And we do two assessments there again. The pollutant health effects. What are those health effects? And this is qualitative. This doesn't have numbers to it. And then the second thing we do is we do estimate, we have a numerical estimate of how toxic it is when we breathe it. So when we do we go to the next slide. When we do that first step, the health effects, which sometimes we call the hazard characterization or hazard assessment, we ask a couple questions. Does the pollutant cause non-cancer effects? And examples of non-cancer effects include respiratory effects, trouble breathing, or effects to the nervous system. We also ask, is a pollutant a carcinogen? And here there are several agencies, and we've highlighted two here, EPA, and also the International Agency for Research on Carcinogens, which we call IARC. They classify substances as to their potential or the likelihood that they can cause cancer. And while they use different words, we pretty much have the same kind of approach to it. So one of the ways we classify cancer risk is it a known carcinogen? Is it known to cause cancer in humans? The second is it likely or probable to cause cancer in humans? The next one, is it possibly a carcinogen, or is there suggested evidence? So as you can see, as I'm going down here, it's the likelihood that it's really a carcinogen is less and less, and that's because we have less and less data to say that it's a carcinogen. And then the next level down is there's not enough data to determine if it's a carcinogen. There needs to be more studies done to determine if it's a carcinogen. So for a known carcinogen or a known human carcinogen, we have we have human data. We also have animal data. It's pretty robust data sets when we call something a known carcinogen. With likely or probable, we have really robust animal data and some human data usually, not quite enough maybe to say it's a known. There's still more work to do in that department, or maybe it's just the end of the road because we don't have human data. And then possible is, well, you've got some animal data, and so it's possibly a carcinogen, but we can't bump it up to say it's more than that. So that's an important part of the risk assessment. What do we think its potential for causing cancer is? And then we want to know what kinds of cancer it causes. I mean, different types of cancers through inhalation can vary. So we have lung cancer, which is associated, for example, with exposure to chrome-6, we call it, or chromium. Leukemia is associated with exposure to benzene, and leukemia is from it's white blood cell cancer. For ethylene oxide, inhalation exposure may be associated with breast cancer in women and lymphoid cancers, including non-Hodgkin's lymphoma, myeloma, and what's called lymphocytic leukemia. And I know a lot of you guys have already done a lot of work on this, and this is familiar to you. So once we know what kind of general health effects it can cause, cancer or non-cancer, how likely we think it is, what's the weight of the evidence for determining that it's going to cause cancer for sure or possibly, and then what specific cancers it cause, then what happens is we do the numerical estimate of toxicity. And these are done usually from our Office of Research and Development here at EPA, and other agencies do too. The state of California does them, the state of Texas does them, different countries do them, several organizations do them. And developing a numerical estimate of toxicity is a very large undertaking that takes years, and it's well beyond the scope of this presentation. We're happy to answer as many questions as you have about the details. But in this short period of time that I've got with you today, I'd like to just describe below some terminology and some key points about toxicity assessment that we'll come back to as we talk about risk results and going forward both at the meeting next week and any future discussions that we have. So it's a little bit of, of a reference guide, I guess. So to calculate risk, EPA needs to have a numerical understanding of how toxic a chemical is. How much of it do I need to breathe in before I have an adverse effect? For a carcinogen, we use a number, and it's actually an analysis. It gets boiled down to a number with a whole lot of words around that number. But the number itself is called the unit risk estimate, and for shorthand, we just call it a URE. And it's developed looking at all the toxicity studies about a chemical, both animal and human. And the human studies are usually worker exposure. That happens unintentionally, of course. And sometimes, some pollutants we have worker exposure for, and not all of them. For ethylene oxide, we actually do. And so the unit risk estimate, and this is kind of a not simple concept, but it's the estimate of the increased cancer risk from inhaling a concentration of 1 microgram per cubic meter of a chemical for a lifetime. So it's the risk of getting cancer if we were to breathe that for 70 years, which we equate to a lifetime, even though we know people live longer, for 1 microgram per cubic meter. And this might become more clear when we do the math at the end. You can see how it works. So because exposures in the studies, here's an important point that we always need to know, and is relevant for ethylene oxide, is that because exposures in the studies that we use, both the animal studies and the human studies, are usually much higher than what people breathe in the neighborhoods living around facilities, we have to use another model, different mathematical models to extrapolate from those high doses that the animals are given and the higher doses that the humans unintentionally breathe in the worker studies down to the lower doses that we see around in the neighborhoods around the facilities. And so that's an important thing just to keep in mind. If the pollutant is mutagenic, that means it causes changes usually to the DNA, then that means that it's more toxic to kids, to children. And so we add what we call an age-dependent adjustment factor for the unit risk estimate. And the and ethylene oxide is mutagenic. So at the end of the day, we multiply this unit risk estimate by a factor of 1.6. We can walk through how all that's done if you want, but I'm trying to cover a lot of material in a short period of time, so you'll see when we do the calculation, which we are about to. So putting it all together, again, at the end of the day, it seems really simple. Exposure times toxicity equals cancer risk estimate. As you can see, there's a lot that goes into the exposure side and a lot that goes into the toxicity side, but at the end of the day, there's a multiplication that we do. And so if we go to the next slide, we'll walk through an example. So they'll define the risk characterization first, then we'll walk through an example. So as I just mentioned, exposure concentration times the unit risk estimate equals the cancer risk. Again, for our cancer assessments, EPA typically assumes that a person is exposed for 70 years. And we will do 3 calculations in our risk characterization. The first one is called the maximum risk. This is the increase in the lifetime cancer risk at the location of the highest concentration where people live. So we look at the model, and the model has a bunch of concentrations laid out over that 50-kilometer area, or 50 kilometers from the facility in all directions. And there is a highest concentration that we have in an area where residents live. And so that concentration we will then multiply by that unit risk estimate, and that turns out to be our maximum risk. And I'll show you how to do that on the next slide. So that's the first thing we do. Now, we also sometimes call this a maximum individual risk, but I want to be really clear that this isn't a real live individual. There's not one person out there that is the maximum exposed individual. It doesn't represent an actual person, but it represents the highest concentration where somebody could live or is likely to live. So that's the first calculation we do, this maximum risk. So the second thing we do is we calculate the numbers of people in the modeled area at different risk levels. So we'll have people like at or above 1 in a million, at or above 10 in a million, at or above 100 in a million, for example, to get a feel for how many people are at each risk level. That's an important factor when we do regulations. We want to know how many people are exposed in addition to the maximum. And then we also do incidence, and these are estimates of possible cancer cases per year, and then we also do it over the 70 years. And I want to make sure that I'm clear here also. So this is a predicted incidence. I know that the state of Illinois, the Public Health Department, did that cancer study that they talked to you guys about, and that was actual recorded incidence of actual cancer cases. So that was real cancer cases looking historically, and that's not what this incidence is. This is looking forward and estimating what the possible cancer case scenarios are going out to up to 70 years. So that's an important distinction to keep in mind. So for, let's do an example. So we've got a unit risk estimate for chemical X, and let's just say that it's 1 times 10 to the minus 4, so, which is a number. So that's per microgram per cubic meter. So your risk, my risk, anybody's risk is 1 in 10,000 essentially for every microgram per cubic meter, a small concentration that we breathe, if we were to breathe that constantly at that same level for 70 years. And so that's this unit risk estimate number. So because chemical X is a mutagen, we apply this age-dependent adjustment factor, and so we end up, it's not just 1, it's 1.6. So you times the 1 microgram, 1 times 10 to the minus 4 times 1.6, which equals 1.6 times 10 to the minus 4. So that then becomes the unit risk estimate. And again, we don't do that with all the pollutants, and we don't have a lot of pollutants for which we have these age adjustment factors, but ethylene oxide is one, and so is chemical X. So to get cancer risk, we multiply the unit risk estimate by the long-term average concentration in micrograms per cubic meter. So if we have, for the sake of the example here, we've got the long-term average concentration of chemical X is 0.56 micrograms per cubic meter, and you multiply that by 1.6 times 10 to the minus 4 per cubic meter. If you're a math person, you'll see right away that those units drop out, and what you're ending up with is 4 nines and a 0, which is essentially 90 in a million, and it's a probability, so it's unitless. Yeah, did I say 4?
4 zeros and a 9.
Oh, 4 zeros and a 9. Thank you. So that risk is, for example, it's 90 in a million. Or if you're thinking, or 9 in 10,000. So it depends on how you like to do the math. So, and again, this results in an estimate of the increase in the excess lifetime cancer risk for a person who's exposed to chemical X from that particular facility. I should have put that on the slide. From that particular facility. So it's on top of risks that we normally, the other risks that we have of getting cancer from other sources. So that, at the end of the day, is the math part of it. So how to read a risk assessment. So next week you'll see a table probably very similar to this one, and so I'll just walk you through how to interpret or how to read it. So usually we have several columns. We've got this maximum individual risk, and again, it's not a real individual; it's the highest concentration. We have what we call the risk driver. What chemical is responsible for the majority of the risk? And sometimes there are several chemicals, and sometimes there's just one. The Willowbrook facility for Sterigenics only emits ethylene oxide, so you're just going to see one chemical in that column, and it's going to be ethylene oxide, obviously. We also look at the cancer incidence, as I said, that's predicted, and in this table we've got it per year, and we'll probably add the 70-year one also for next week. And then we also look at populations at or above certain risk levels. So here we've got 4,000 people at greater than 10 in a million, and 100,000 people at greater than 1 in a million. Since the risk is 90 in a million, we don't have anybody greater than 100 in a million. Making sense? So that's what we'll see. So for this example, we got the maximum individual risk at 90 in a million. The risk driver is chemical X. It's the only one we looked at. The cancer incidence is 0.05 cases per year, which doesn't make a whole lot of sense. So when we get numbers like that, what we typically do is we'll say, okay, well, how many cases, how long will it take to get one case of cancer? In this case, it's one case every 20 years. And then again, the population would be 4,000 people that have a risk greater than or equal to 10 in a million, so somewhere in between 10 and 90. And then the last column is people at or above 1 in a million, which is 0 to 90 in a million. So that's the table. The last slide is a graphic that we use to, and some of you have probably seen these with other assessments. So what we have underneath all those colors and those circles is the area that was modeled, or most of the area that was modeled. And then you can see that there are different colors. The yellow is in the middle, and there's a yellowish green, and then another green, and the colors kind of go out from there. And those represent different cancer risk levels. And not surprisingly, the yellow represents the higher risk level because the MIR location is what that arrow is pointing to. So the facility's in there pretty close to that MIR is my guess on this example. And so you see in this area, and everywhere in this area, that these risks are up to 90 in a million. These are around 90 in a million. And then you go out and you've got a ring that's about 80 in a million, and then 70 and 60. So you can see, you can look on the map and look at a location and then look at the color, and you can see what the estimated risk level is at that area. And so that's a normal way we present information in different communities. So that ends the slides, and I think we're headed to
Yeah, so give us just a second as we compile the questions, and then we'll start going through the questions. So if you have additional questions, go ahead and type them into the box. All right, so our first question for Kelly is how, for 70-year exposure risk, does EPA consider the increased risk to young children being exposed?
Right, and yes, and so that's the part, and you probably, the person probably asked that question before I hit that slide. So that is the age-dependent adjustment factor. So for children ages 0 to about 2 years old, we apply a factor of 10. So we say that the chemical is 10 times more potent at that exposure time frame than it would be for a grown-up. For 2 to 16 years, we apply a factor of 3, and then at 16 and above, you just apply a factor of 1. And so, as it turns out, if we apply the age-dependent adjustment factor, it ends up that we just multiply that unit risk estimate by 1.6, and that provides protection to children. How many pediatricians, children, environmental specialists are involved in the risk assessment development? We don't have them involved. When our risk assessments are based on methodologies that have been applied over the years. To the extent that there is information about children's risk, when our Office of Research and Development develops that toxicity value, there are experts in children's health on there making sure that that value appropriately characterizes the effect on kids. And then in our shop here, we apply those values and then discuss the fact that this pollutant may be more potentially toxic for children when we do our write-ups.
The next question, are dispersion models three-dimensional? Do they estimate concentrations by height?
Yeah.
Yeah, so they do, and that helps us to understand how dispersion happens as well.
Right.
And Smith is going to expound on that a little bit.
A little bit. So there's a couple different ways that the model takes into account height. One is the meteorological data that we use. There's what's called an upper air station and a lower air station. So they're accounting for different weather patterns at different levels of the atmosphere. And then when Kelly was talking about the input to the dispersion model, she mentioned emissions and locations of those emissions, and the height of those emissions is also very important. She talked about the stack emissions and the fugitives, and so we include the height of those emissions in the dispersion model, and then the various levels in the atmosphere that the meteorology carries that plume through the air in its dispersion.
Yeah.
All right. So there's an understanding that the UREs are estimated conservatively, so as to avoid an underestimate of potential risk. Also, EPA's risk assessment generally states that the URE is the upper bound estimate, and the actual value is likely lower and may be in fact 0. How does EPA incorporate this conservatism into the risk assessment, perhaps?
So this idea that it's upper bound and actual value is lower that's designed to be protective of the most susceptible person. So my risk I may get cancer from a particular exposure because I'm that upper bound person. and Laura may be 0 because her immune system is totally different than mine. So it's not, we don't expect that it's 0 for everybody, but it's 0 for some people. So, but it's true that we want to err on overestimating versus underestimating potential risk. But again, based on the cancer risk assessment guidelines that have been in place and evaluated and redone a few times since the mid-'80s, we think that it's a reasonably health protective scenario and not a terrible overestimate. I mean.
So, are you assuming the 70-year exposure in Willowbrook's risk analysis, or the shorter time period from the ATSDR report from last year?
Well, we do 70 for sure. That's what our bread and butter is, 70.
And ATSDR for their purposes?
They use a 33-year, I think, exposure.
Yeah.
So,
and I think it's important to remember that the different analysis are looking at different things. And so next week when we talk about the different studies that are being done, I think it'll be clearer, we do a regulatory analysis, they're doing a different type of analysis, and that's why the time frames are different, because we're looking at different things. These risk calculations are the same that were used in 8/21, 2019 letter that began this journey, yes or no?
It's a similar approach. So I believe that 821 letter is the ATSDR letter, and while that wasn't our work, the general approach to risk assessment is very similar, although as we just mentioned, ATSDR tends to use 33-year exposure and we tend to use a 70-year exposure.
So you mentioned that the number of the people living near the facility is taken into account for the risk assessment. Is the fact that the facility is located in close proximity to multiple schools a factor in the assessment?
I think, well, the question is about, are we concerned about children? Yes, of course, and that's why this 1.6 factor is we absolutely use it. But what we're looking at is we're looking at wherever those maximum exposures are. We want to see what the risks are.
So some people have multiple cancers themselves, or multiple cancers in their household. How does the risk assessment look at multiple different cancers?
We can't put that fine a point on it in this assessment, and with the information we have, the unit risk estimate covers several cancers, as we mentioned, some of the lymphomas and the breast cancer in women. So we can't parse it too much. We just say that if somebody's exposed for 70 years, they have an increased risk of getting these certain kinds of cancers.
So is it fair to say, Kelly, if we can't say that the Smith family who lives across the street is going to get breast cancer and lymphoma and such and such and such and such, or the Jones family who live on the other side of town is going to get a different type of cancer? We don't have the information to make a direct link from the emissions to a specific cancer.
Right, which is, we can't. That's not, we don't have the information to be able to do that. And so what the question that the risk assessment can't answer that one, but the question it can answer is, what is the Jones and the Smith family's increased risk of potentially getting these kinds of cancers? And that's as far as the information goes. And in the regulatory world, EPA uses that information to set regulations for air pollution controls and emissions reductions. How is sorry, this is Kelly again. How is the risk assessment using the IDPH cancer study showing increased cancer for women and children? So the Illinois Department of Public Health cancer study is very different than our study. So they looked at cancer registry data, sort of retrospective for year historically, and asked the question, what cancers are in the population that and are they higher or lower than one would expect? So that was looking sort of historically. What we do is we are looking forward. So we start at today, or whenever we do the risk assessment, and we estimate the potential cancer risk going forward for a period of 70 years.
Can you use the risk formula to calculate risk based on shorter exposure times in years, say a total exposure for only 5 years?
Yeah, sure. You could do whatever number you want. We tend to do a lifetime because that's what pretty much that's what the Clean Air Act tells us to do.
Okay, so I'm living on the border of the less than 90 and having my children here since 1999. How can I calculate the risk?
Well, I mean, you want to walk through the... Yeah, I mean, we can use whatever years you want. But I don't know if she's asking, or he's asking to walk through an example.
Yeah, that might be one that next week when they're open house, it might be worthwhile sitting down and having some clarifying conversations so that we kind of get a better sense of what the need is there.
So how do we compare the risk assessment value to published cancer rates used by the Cancer Association? So without having more information on that, I would guess that that's our background, like the 1 in 3 that normally we get. That's the American Cancer Society says we all have about a 1 in 3 chance of getting cancer. So this is adding to that, but it's not, it's on top of that. So this excess cancer risk, these predicted whatever, for this example, the predicted 1 case in 20 years is in addition to that. But that's for the entire population.
Yeah. Yeah, so the next one is the Children's Health Protection Advisory Committee consulted on the risk assessment. That's an important part of the inter-office, the interagency review process, and so they have a chance in our regulatory process to review all the information that goes into the decision making, and since part of the risk assessment informs the regulatory questions that they would be involved with that. Understanding that this is not necessarily the case in Willowbrook where the only exposure is ETO, how does EPA consider cumulative and synergistic impacts of multiple facilities and other pollutants simultaneously impacting a community?
So there's a couple of things on that. So the NADA, the National Air Toxics Assessment, does, at least at the census tract level, look at risks from multiple different kinds of sources. So and it's a screening assessment, but it gives us a place to start to look. Wait, so I'm getting... But when we do the risk assessments for our regulatory program, or one that we do, the kind that I've described here, is we follow what the Clean Air Act tells us to do, and which is we look at all the pollutants coming out of a particular industry sector. So let's just choose petroleum refineries. And so we will look at, I don't know how many pollutants come out of petroleum refineries. We did it a few years ago. A lot. 100 maybe. And we actually add up all those cancer risks. We think we look at cancer as cancer, not lung cancer versus breast cancer versus another kinds of cancer. So we'll do that for the surrounding area that we model. Now, if there are 2 petroleum refineries that impact the same community, we will add those impacts together. If there's a petroleum refinery and a chemical facility, we don't do that because we can't do that. Our regulations are designed to apply to industry sectors as they admit. So what we do is we ratchet down on individual facilities, individual industry sectors, but it's a sector-based approach, regulatory approach.
So I think there's a clarification that people are asking for the example that you put that we put up. So let me go back to that and. So I think what we're going to do is we're going to go back and look at the math and make sure, because this is not looking right to us, and so we'll look at it and see again what it is, because the question's really not it's not clear to us.
So here's what risk assessment is being done to protect ethylene oxide's highly explosive nature. That's a different. We can look into that. That's a different program, but we can chase that answer down. We do human health risk here from chronic exposures.
Okay, so we're getting down to 9 minutes till. Let's see if anybody has any more some additional comments. Okay. So the next one is, what is EPA doing to help encourage safe alternatives that already exist and are FDA approved to phase out dangerous carcinogens in such close proximity to homes and schools and shopping centers?
This is Mike Kerber. Just a couple of things to note. One is federal EPA is working very closely with state EPA and trying to come up with an appropriate long-term solution for this community, but also across the federal government. US EPA is talking with other federal agencies like FDA who have a stake in this issue, and we are trying to coordinate with them and have a consistent response across the federal government. So we don't have anything specific on that, but it is worth noting that we are coordinating, collaborating with FDA.
Okay, so I understand that the age adjustment factors you explained for 0 to 16, does EPA consider ETO exposure in utero?
I will get a better answer than I can give on that. I know we don't, and there's the reason why I can chase that down. I do know that in the recesses of my brain, but I don't. I want to double check with our head toxicologist before I answer that one. But I'll get an answer.
So we got is anyone or the industry or stakeholders getting a preview of the risk assessment before the meeting? We are still working on the risk assessment, and the idea is to potentially, hopefully, get an executive summary out to folks to help people prepare questions, but we don't think we'll get it done in time to get it out before the meeting. So, I think there's a lot of questions about the risk assessment for miscarriage and in utero and birth defects, and that kind of stuff. And I think we need to really consult with our Office of Research and Development folks to get a better understanding of how they set I just lost the
well,
the
what
word.
I can say about that is that the data that drove that unit risk estimate were the cancers. If the miscarriages and birth defects were caused at a lower concentration than what those cancers are, then the unit risk estimate would have been based on miscarriages and birth defects. I don't know for a fact that there's any data on miscarriages and birth defects, but the unit risk estimates are developed based on the effect that happens the soonest at the lowest concentrations. So that being said, the idea is if there were data on miscarriages, for example, the unit risk estimate would be protective of that because it's protecting even at a lower level. But I don't know, and I can find out what in that data set, in those many, many, many studies that are on ethylene oxide, if any of them are on miscarriages or birth defects. And you're exactly right, Laura, we'll go to our Office of Research and Development and ask them that.
Okay, so we still have some confusion on how to do the risk adjustment factors for the age group. So, and I think people are getting confused with the math. So, Amy, do you want to kind of walk through that a little bit?
Sure. As Kelly explained, we separate out the different age ranges, and for ages 0 to 2, we apply an additional protective factor of 10. So anybody ages 0 to less than 2 years gets an additional factor of 10 added to the unit risk estimate. For ages 2 to less than 16 years, the age-dependent adjustment factor is 3. So that's added, that's multiplied by the unit risk estimate. And then for any ages greater than or equal to 16 years, there is no age-dependent adjustment factor. So if you multiply by those and for over 70 years each, if you do a multiplication over 2 out of 70 years, 14 out of 70 years, and 54 out of 70 years, with those factors, you end up with the unit risk estimate that EPA uses, and that is 5 times 10 to the minus 3. And we can bring something in writing that you can see for the meeting.
Yeah, I think that would be helpful if we maybe put together a table that walks people through that.
And the same approach could be used for something like what the what ATSDR does, and that is for a different length of time, so 33 or 35 years.
Will age stratification be reported or just one overall number? We typically just do one overall number. And again, these are risks. These are estimated risks over a population. So this isn't a risk that I could calculate. It wouldn't be meaningful to calculate it and put too much faith in it if I'm trying to calculate it for me or my kids or something like that.
Okay, so I think we're going to wrap it up for the day. We've got some still good questions here. We do have the open house next week before the meeting, so make sure you bring your questions with you to the open house. And Kelly and Darcy and folks will be there to be able to answer your questions. In the meantime, we're still working on this assessment, and our goal is to get an executive summary out next week so people can have it ahead of time. But we're still, like I'm saying, we're still working on the assessment, so we hope to get it there. But we look forward to seeing folks next week, and if you have other questions or you need anything, feel free to call me, Laura McKelvey, at 919-541-5497. Thanks so much for your time, guys.